Welcome back, students. Today we are going to start a fresh topic from Unit 2. Of course, we finished Unit 1 in the last lecture. So today we are going to discuss a new topic that is homomorphism. The word homomorphism we have seen and read in the last semester related with group theory. And the identical thing is here also in a ring. And because we have two operations in rings, so it is natural to talk about something which is preserved algebraically and something under which the specific features or the features are preserved. Okay. Basically, when we talk about an isomorphism, so by isomorphism, we establish that if there are two objects or two things, they are algebraically identical. And when we talk about homomorphism, then we mean by homomorphism that they are retaining certain of its feature. Okay, so being identical is different, and being homomorphism is another thing. Okay, so isomorphism, you know that they may be looking different, but algebraically that is their elements and property. Okay, of course we may write in different way, but they have the same properties. Okay, but in case of homomorphism, we talk about the preserving of some certain kind of operation. Okay. So just like in group theory, if uh, we have two groups, G1 and G2, and phi and is a function from G1 to G2, we say that this is a homomorphism if for any two elements of a G1, we can write like this: if AB equals to phi of A, okay, and phi of B, where star is the operation of this group, okay, and a dot is the operation of this group. Okay, so this is what we know, but additional operation in a ring forces us to consider something more. Okay, so this is in case if the group is multiplicative. In case the group is additive, then we used to write like this: phi of A plus B is equals to phi A and star phi of B. Okay, where star is an operation on G2. Fine. So on considering both the things, here we can show it diagrammatically how that if A plus A and B are in this R1, there are two. If there are two rings R and S, if there are two rings, namely there are R and S, there are two rings. And if suppose, for example, if A and B belongs to R, that is AB belongs to R, okay, then certainly because R plus is an abelian group, then A plus B is also going to be a member of R. So we can talk about phi of, suppose we are defining some function phi from R to S, okay. So this function phi takes A plus B, okay, and this is equals to some phi of A, phi of B, okay, and then because there is another operation, and since R dot, that is a ring under multiplication, is also closed, so naturally A times B is going to be in R. So when we are taking the product of these two, then this is going to be equals to phi of A times phi of B, like this. Fine. Phi of A times phi of B. So these two things need to be considered when we are talking about ring homomorphism. So before proceeding that, let us see what is the official definition, and then we can take up some examples today. So definition, that is, it says that a ring homomorphism a ring homomorphism. Suppose, for example, phi from a ring R to a ring S is a mapping from R to S that preserves the two ring operations uh, that is phi of A plus B equals to phi of A plus phi of B. Of course, this operation is the addition, okay, of S, okay, and you know that not it is not always that S has to be integers on all, okay. So this operation is need to be considered in S, and this operation need to be considered in R. So this you need to take care, okay. I don't think this plus and this plus and this plus same, okay. This is not same, they are not same, and of course they are same only if R and S are of the same nature, okay. So another property that A times B, and this should be equals to phi of A times phi of B. Okay. And this should be true for all A, B belongs to R, the ring R. Fine. So in group, we used to verify this much only. And in case of ring, we need to verify these two. So there are examples. Let us see. If you see the example, there are some examples in your book, and except that, let us take some more example. Okay, we can take for example that let phi from Z to Z, that set of integer, okay, be defined by phi of x equals to 0 times x, okay, phi of x equals to 0 times x. Or identically, this is, you know, that 0 times x is nothing, but in a ring, identically, this is going to be 0. Fine. So this is sometimes called the trivial homomorphism. This is called trivial homomorphism. Okay. So this is a homomorphism. Later, this is defined by this. Then phi is a homomorphism. And phi is a homomorphism because you are taking if two integers in Z, of course. So this is going to be 0 times x plus y by definition, and this is equals to distribution of multiplication over addition. This will give us 0 times x plus 0 times y, and this 0 times x is nothing but by definition phi of x, and this is phi of y. Okay, so we have this phi of x plus y is equals to phi of x plus phi of x plus phi of y. So one thing we verified, and another thing we can take like phi of x times y, and by definition this should be phi of 0 times xy, and of course we can write it like 0 times x, okay, and 0 times y, like this, 0 times x, 0 times y. So what we can write here, this 0 times x is phi of x, and this is phi of y. And this is of course true for all xy belongs to R. All right. So this phi, the function phi is a ring homomorphism. So next, let us consider an example number 2. If you are taking phi, or let us define, okay, define phi from z to z by how we are defining phi of x equals to 1 times x, okay. Then phi is a homomorphism. Phi is a homomorphism, okay. So I think you can verify it. There is absolutely no problem. One thing is one thing we can note it down when we are considering from z to z. Okay, when we are considering from z to z, uh, z to z, okay, phi from z to z, by how we are defining phi of x equals to a times x, okay. So we have taken the two choices for A, and that choice is 0 and 1. There are two choices we have taken. Okay. And the property of these two elements are, okay, properties of these two elements are, is that 0 square equals to 0 and 1 square equals to 1. Okay. So 0 and 1 are what? Idempotent? Idempotent elements. Idempotent elements, okay. So in both the cases, for the choice 0 and for the choice 1 here, this comes out to be, this function comes out to be, or we were able to prove that they are, in both the cases, phi is a ring homomorphism. Phi is a ring homomorphism. But the question is that, so what we got? We got two homomorphism from Z to Z, from set of integer to itself. There are two homomorphism. Is there anything else? Any map which makes this as homomorphism? Okay. So for this, let us consider something. If you take, for example, phi x equals to 5 times x. Phi x equals to 5 times x. So phi of x plus y, how we can write? Phi of x plus y. So this is a phi of x plus phi of x, phi of x. And certainly this is going to equal to phi of x plus phi of y. So this is satisfied. And what about if we take a product of these two? So we have to write phi of x times y, and this is equals, and this is not equals to phi of x times phi of y, you know, this is not equals to, okay. And of course this is phi of x and plus phi of y. So therefore what we conclude that, and this is possible because if we are defining this, this is going to certainly hold, okay. But in case of multiplication, there is a problem. The problem is with this, because we cannot factor or square 5 to keep it unchanged. Just like here we have done 0 square is 0 and 1 square is 1. So it is not changing. Okay. So that's why we are taking benefit of this, and we are able to say that phi is a homomorphism in these two cases. Fine. So in case of Z to Z, is there any other option it can have so that it becomes a homomorphism? Hello. Is there any other option? No, because we have taken this example. Except idempotent element, this phi cannot become. Okay. So what we note that there are exactly two homomorphism. Okay. Two homomorphism. There are exactly, I think, yeah, exactly two ring homomorphism. ring homomorphism. You should write ring homomorphism from Z to Z. Okay, so this you should note it down. But now question is that is it true for all? If you take this idempotent, then they are going to, this map is going to be a homomorphism. In general case, when we replace Z by other rings, in general the answer is negative, that it is not. But thing is that they becomes candidate for a ring homomorphism. Okay, they becomes candidate for ring homomorphism. So just like if you remember, when you have studied maxima and minima, and you need to find the critical points, and then you are computing the maximum on those points. So maximum, being your maximum critical point was not guaranteed that on each critical point you are going to get maximum. Okay, but thing is that the result is otherwise. If it is maximum, then you are going to get that point is going to be a critical point. Okay, so what we used to do, we used to find that all critical points, and then we need to compute whether it is a maximum or a minimum. We need to verify for that. Okay, so being a critical point doesn't mean that this is going to be maximum or minimum at that particular point. Okay, so this is the thing. So here also, so they are becoming the candidates. They are becoming the candidates if we are taking what we say that idempotent element. Okay, so next example, let us see example number 3. Example number 3, we can define phi from Z2 to Z10. Okay, by how we are defining phi of x equals to 2 times x. Now you know that 2 square equals to 4. 2 square equals to 4. Okay, 2 square equals to 4. So since 2, this is not equals to 2, and therefore it is not an idempotent element. So this is not going to be a, okay, this is not going to be an isomorphism, homomorphism. Okay, not homomorphism. Okay, as 2 is not idempotent. Okay, so अगर idempotent नहीं है तो हम तुरंत कह देंगे कि वो होमोमॉर्फिज्म नहीं होगा. अगर है तो फिर पॉसिबिलिटी बनती है कि वो होमोमॉर्फिज्म हो जाएगा. समझ रहे हो ना? Are you getting what I'm trying to say? Being idempotent doesn't imply that this is going to be homomorphism. Okay, but if it is not an idempotent, then it is guaranteed that it's not going to be a homomorphism. Thing is that. Okay, and of course you can check it out. Phi of course 2 we can sum is okay, or sum is okay, but when you are talking about product, then if you're writing phi of xy, then this is going to be equals to 2 times of xy. Okay, so this is not equals to 2 times of x, 2 times of x, 2 times of y. Okay, because this is equals to phi of x and phi of y. So this is not homomorphism. Okay, अगर 2 को ऐसे ब्रेक कर लेते कि 2 का स्क्वायर क्या हो जाता, 2 हो जाता, तब बात बच जाती. ठीक है ना? तब बात बनती, मतलब पॉसिबिलिटी तब हो रही थी. अदरवाइज जरूरी नहीं है कि हम अभी देखेंगे आइडेम्पोटेंट एलिमेंट होगा, बट यू कैन नॉट क्लेम दैट अगर आइडेम्पोटेंट हो गया तो फिर हो ही जाएगा वो. ठीक है ना? होमोमॉर्फिज्म. अगर होमोमॉर्फिज्म नहीं है तो फिर वो सॉरी, अगर वो आइडेम्पोटेंट नहीं है तो इंप्लाई कर देगा नॉट होमोमॉर्फिज्म. ओके, so what we see here, not idempotent, okay, implies not homomorphism. Okay, not idempotent implies not home, but अगर आइडेम्पोटेंट हो गया idempotent implies candidate of homomorphism. Okay, that is a possibility. Okay, that is there is possibility of homomorphism. Okay, so this we should note it down. Let us consider next example, example number 4. Let us define phi from Z4 to Z10 by, we are defining it, phi of x equals to 5x. Okay, phi of x equals to 5x. Okay, and this 5 is a member, will be treated as a member of here Z10. Okay, you should remember this 5 should be treated as member of Z10 because this is in image domain. Huh? So here you see 5 square equals to 25, and in Z10 5 square equals to 25. 5 here in Z4 becomes identity, you know. 5 in Z4 becomes identity, multiplicative identity. So here 25, and when we divide it by 10, we will be getting 5. So 5 square equals. So here this implies that 5 is idempotent. Idempotent. Okay. 5 is idempotent, but 5x equals to 5x is not a homomorphism. Whenever I am using here homomorphism, it means that I am talking about ring homomorphism. Okay, not group homomorphism. Okay. Hello.
Yes, sir.
Just a minute. Just a minute. Okay, so why it is not homomorphism? You can check it out. 5 of x times y you can take. Okay, and this product is in Z4. Okay, here 5 times of xy we are taking product in Z10. This should be you need to take care. Okay, you need to take care of this. Uh, just a minute. 5 side potent. No. Here in case it will become, I think, a homomorphism. Let us see. But we have some example. Okay, phi is a homomorphism. Okay, because 5 of xy, we can write 5 of x and it 5 of y, and 5 square, you know that nothing but 5. So this is equals to 5 of x and 5 of y. And of course, this thing phi of xy equals to 5 of x plus y. This is certainly going to equal to phi of x plus phi of y, like this. Okay. Okay. Let us take another example where we have idempotent, but it is not homomorphism. Okay. So consider phi from Z5 to Z10. Okay. Defined by 5 of x, phi of x equals to 5 times x. Okay, so as before, 5 square equals to 25, and this is equals to 5. So this is idempotent. Idempotent. Okay, fine. And of course, you know that it is idempotent. All right. So we have a 5 of xy, phi of xy equals to phi of x, phi of y. So this is verified. But what about addition? In addition case, phi of x, uh, in addition case, if we take just a minute, if we take Okay, we need to add any two elements now. We need to add any two elements here. So phi of, we are taking that 4 plus 1. If we are taking, for instance, we are taking x and y different. We are taking x, y to be different. No? So here 4 plus 1. So this is equals to 5, phi of 5, and phi of 5 is 5 of 5, and 5 is here in Z5 is 0. 0 as 5 equals to 0 in Z5. Okay. Okay, it's all right. So by definition, this phi of 0 is equals to 5 times 0, and this is equals to 0. Okay. So phi of 4 plus 1 is becoming 0. Okay. This 5 of this is 0. But you know that a 5 of 4 plus this, and if you write, if it is a homomorphism, then we can write like this: 5 of 4, phi of 1. So phi of 4 is what? 5 times 4, and this is 5 times 1. This is 20, and this is 5. This is equals to 25. And a 25 is under modulo 10 equals to 5. Okay. So here 0 is not equals to 5. So this means that this is not a homomorphism. Okay. So here phi is not a homomorphism. Okay. All right. So to do this, these things, let one thing. Let me make it clear with some example. One more example. Here we will be discussing the possibilities of item. What we say that homomorphism. Okay. So if we have been asked how many homomorphism phi from Z4 to Z10. Okay, Z10. So this is the question. So what we need to find the idempotent elements in Z10. Okay, idempotent. जो idempotent नहीं होंगे तो उस केस के लिए phi of x equals to ax. ये तो होमोमॉर्फिज्म होगा नहीं अगर ये आइडेम्पोटेंट नहीं हुआ, वो चीज हम देख चुके हैं, ठीक है ना. अगर ये आइडेम्पोटेंट हुआ तो ये भी नेसेसरी नहीं है, ये भी हम देख चुके हैं कि हो ही जाए होमोमॉर्फिज्म. ऑल राइट. ओके. सो इफ it is becoming idempotent, then we need to discuss them in detail. Okay. Then the idempotent elements in Z10 are, what are they? 0, 1, 5, and 6, like this. Okay, these are the idempotent elements. You can check it out in Z10. Okay, so possibility of ring homomorphism. Okay, so what are ring homomorphism? What are the possibilities here? So possibilities are, first, let us see. The first possibility is phi of x. Okay, let us write like this in general. Okay, with the choice a equals to, a can take 0, 1, 5, and 6. There are 4 possibilities for a. So of course for 2, 0, and 1 we are done. Okay. Okay. Clearly that is phi of x equals to 0 times x. ये होगा phi of x equals to 1 into x. ये भी होगा, ठीक है ना. and then phi of x equals to 5 times x, and a phi of x equals to 6 times x. So among these two are certainly going to be, as we have seen. Are you sure about this? Hello. This is all right. No, this is all right. What about this? Is this going to be naturally? Hello. Hello. So this is a big question here. So how this depends on the domain. This depends on the domain. We have taken Z4 and 10. Okay. So in case of Z10, if we are in case of Z4, if we are taking phi of 1 plus 1, so here it becomes 0. You know that a phi of 2 and a phi of 2 is nothing. In Z2 is 0. Okay. Z2 is 0. Z2 is 0. And you know that in this is this is 0. So just a minute. This is equals to, by definition this is going to be equals to 1 times 0, and this is equals to 0. Okay. But you know that phi of 1 equals to 1, phi of 1, just a minute, phi of 1 plus phi of 1. So this is equals to phi of 1 is 1 times 0 times 1 times 1 times 1. No, you're taking 1, then this is going to be okay. We need to take another example, I think. Okay, let me take another pair of element we need to take. For example, let us take a 3 plus 1. Okay, 3 plus 1 is phi 4, and 4 in Z4 is 0, so phi of 0, and this is 1 times 0, so this is going to be 0. Okay, so here phi of 3 and plus phi of 1, this is equals to what? They should be equal, both should be equal. So phi of 3 is 3 times 1, no, 1 times 3, and plus 1 times 1, this is equals to 3 plus 1, 4. Okay, and a 4 is not 0 in Z10. Z10, I think. Yeah, in the right hand side we have Z10. Okay. Okay. So you see here that this is not a homomorphism. This is not naturally identity map. Even is not going to be homomorphism. Okay, identity in the one sense that if they are the same, if they are here Z4, if we are having here Z4 also, then you will be getting naturally. But if they are not same, different, then this is not going to be. Okay. So 0, 1 is okay, but 1 times x is not necessarily when we are talking about ring homomorphism from Zm to Zn. Okay, Zm to Zn. And this is you can verify that this is a homomorphism, and in this case, this is also not a homomorphism. And for example, you can take some pair of points in it. Okay, and then you can verify. So there are exactly, in fact, two homomorphism. One is this one, and another is this one. So what we need to find? We need to find out the idempotent elements in the codomain, and then we need to consider this kind of function. And then for each choice of A, we need to verify whether or not they are becoming homomorphism. Okay. Okay. So once what we have until now, the clarity that a phi of x equals to 0 times x, दिस इज ट्रिवियल, तो एक तो एग्जिस्ट करेगा ही ना, ठीक है, ट्रिवियल होमोमॉर्फिज्म, दिस इज trivial, this is trivial homomorphism. Okay, now next the question, if you talk about phi from next example, phi from Z6 to Z6, Z6 to Z6. Okay, so idempotent elements are idempotent elements. Okay, what are they? 0 and 1 certainly, and 3 and 4. Okay, 0, 1 and 3 and 4. Okay, so in this case you can verify that phi of x equals to ax, where a is taking value 0, 1, 2, 1, 3 and 4. Okay, they are all going to be ring homomorphism. Okay, ring homomorphism, exactly 4 ring numbers. Okay, so एक सेट से दूसरे सेट पे होगा तो फिर ये चीज है ना, वो करी जाएगी इसमें. I think there are some theorems, properties. Okay, so we will be taking it in the next class on ring homomorphism. So by that time you can also look for what we say that certain examples are there in your book. From example number 1, example number 1 is talks about in your book, okay, example number 1 in chapter number 15. Okay, in book chapter 15. Okay, example number 1, it says that define a map, define suppose phi from z, the set of integers. Okay, set of integers to zn by how we are defining, that some element here k is mapped onto k modulo n. Okay, k modulo n is a ring homomorphism. Okay, so this is simple, you can verify it. Okay, so this map is nothing but phi of k equals to k modulo n. You can verify. I think we have, you must be knowing familiar with the congruent modulo relation. Okay, so you can use that and verify it. Next example number 2 of your book, it says that the mapping from complex number to complex number, from the set of complex number to a set of complex number, and they are defining phi as a plus ib equals to a minus ib, and then they are telling that this is a ring homomorphism. Okay, so these all examples you can verify. And then example number 3, they are telling that they are defining phi from Rx, the ring of polynomials with the real coefficients. Okay, a ring of polynomials with real coefficient into the set of real numbers. Okay, how we are defining? They are defining by fx equals to f1, not f1 but phi. I think I should write. Okay, here. They are right. They are telling that here, suppose here some polynomial is there, px. Okay, some px polynomial is there, and under phi, and this is mapped onto p of 1. Okay, p of 1. Of course, this is going to be a constant number when you are substituting some variable. Okay, so they are telling that is a ring homomorphism. All right. And then the example, and there is example number 4. This was 3, and they are talking about the phi of phi from z4 to zn, and this we have discussed. Okay, in detail you can see in book How they are defined by phi of x equals to 5x. So detail you can get in your book. Okay. Similarly, example number 5, they are defining 5 from Z12 to Z30 by a similar procedure. Okay, and how they are defining? They are defining it by phi of x equals to ax, where I think they are taking a a value of a0, 15, 10, and 25 or 25. Okay, so they are taking these values. Detail you can get in your book. Okay. Example number 6, they are example number 6. They are defining R is a R is a commutative ring. R is a commutative ring. Commutative ring of characteristic 2 or with characteristic 2. Okay. Then 5 from R, ring R to R. This is not set of real number. By how they are defining that A goes to A square is a ring homomorphism. Okay. So other examples are there. Examples number 7, 8, okay, and 9. So you can read them. If you have any problem, we can discuss in the class. Fine.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.